So on your yellow packet, I redid mine so it's nice and pretty, as opposed to the scribbles that you might have seen when we originally did this. So the first 2 pages, again, those are all the parents. So I ended up going through, if you take a look at those like equations that we wrote down, A, H, and K are coming up over and over again. We're really going to look at what is happening with those 3 letters today. We did not look at page 3, so if you just are ready with like a pencil, we should just fill this in because we, fill it in for, for the purposes of your records, right? So just for record keeping. So on page 3, fill in the table. I feel like you've plotted the parent function a bunch of times. You might notice that you don't need the table anymore. You might notice that you can put the vertex. So we're going to start talking about the vertex. The vertex is that point of the V where the decreasing becomes increasing or increasing becomes decreasing. So as soon as, think about it like if you ever watch anyone play billiards or pool, if they bounce the ball off of the side of the pool table, then where the ball hit the side of the pool table is the vertex. Okay, so the ball is kind of like if it bounces down here, boom, and bounces back. It is the vertex is at 0, 0 here in this case. All right. So just put the vertex, and then you notice that there's no number in front of the absolute value, so it's really A is equal to 1. That's why you might see this rise over run being 1 over 1, and that's where we get this increasing on the left and the right from. So we're on page 3. Pretty sure. It was before what you did before. Like if you flip it all the way over. Yeah. In this case, all the output values are positive because absolute value makes every output positive no matter what you input in there. Linear portions of the graph form a V shape. Kind of already talked about this. Meet at the vertex and then increase at or decrease depending on how you're looking at it. At a rate of 1. I'm hoping that a couple things are crossed off on the packet, right? Okay. So you kind of look down below. We're going to be taking a look at a few of the things on there. Do you have your packet? Did you grab your folder? Do you have the yellow front? Thank you. Logan, get your packet out, please. All right, so we're also going to be taking a look at down at the bottom. You need to know about the intercepts. So it's just like a line. If you have a linear function, you look at the intercepts. Where does the function cross the x and y axis? Here we know that the x and y intercept are actually the same value. If you're not sure where any of these things are coming from, then make sure that you're asking me questions. So the x-intercept is where the vertex is, because the vertex is the only point of this V shape on page 3. Logan, I should not have to tell you more than once. Thank you. X-intercept 0, 0. Y-intercept's also 0, 0 because that's by definition where the graph is crossing the x-axis and the y-axis. Domain and range should also be familiar. The increasing and decreasing over the intervals, though, is something that's new, and we might not discuss this too much. I know some people are really trying to see that, sorry. We might not discuss this too much, but we are, there we go. We will just look at where the graph is increasing. Okay, so where does it look like the graph is going uphill? Where does it look like the graph is going downhill for decreasing? And I split the interval. So you'll notice that in the interval starting at 0 on the x, all the way to positive infinity, you have the right-hand side of the V going uphill, and then you have a decreasing situation happening from the negative part of the graph. You just go all the way to the negative infinity on the x, and this graph's going downhill until you get to 0, and it bounces to go back uphill again. So kind of take a look at that. The intervals, the interval from negative infinity to infinity are split. We put 2 intervals. So this is, one more time, from negative infinity to 0, we have a decreasing situation, And from 0 to positive infinity, we have an increasing situation. Okay, I'll go back down there. All right, and we're not really going to discuss, if you get into algebra 3, you get into pre-calculus, you might talk more about end behavior, max and min. We might get into it this year, but I'm not 100% sure. So I didn't want to push it if we might not need it. So then I'm going to kind of walk through the rest of this packet, and I don't necessarily think that you need to sit here and try to copy in what you haven't done. Okay, so I'm fully acknowledging Friday. We have different people getting to different places on this, but try to get the gist of it, of the patterns that are happening overall. We're going to focus in on this letter A, focus in on this letter H, and focus in on this letter K. So I'm going to show you my page 4. At the top that says vertical shift, and I want you to add the letter K up there so that you understand that every time you see K, it's going to be outside the absolute value, and it's going to add K. We're going to shift up or down, so we're either adding a positive K or a negative K. We're shifting the graph up and down. So as you were plotting those V-shaped graphs, you might have noticed that some of them were higher, some of them were lower, but they were basically copy-paste up or down the y-axis. So make sure you write down that a vertical shift at some point is K, and it's outside. K is the value being added or subtracted outside the absolute value. I did color code this. If you do want to see this at all at any point, I linked this on Schoology under today's submission. Or under today's section in the folder for week 16. And then I just crossed out description. That's where you'll see where my tables were. And then I also wanted to point out to you what was going on in each of the tables. So you either can think about this as the physical graph itself moving up and down the y-axis, or you can also think about the values that you have. You have those y values. Those y values will increase or decrease by K in every case. All right, don't try to copy this all down right now. Just try to think about what's happening, understand the pattern for K, and you can copy this. There's going to be time today to do it if you want to. Page 5. If you're looking at a reflection, you'll see a negative. So I made my negative really dark and bold, and then I just put a 1. Because even if we don't see that 1 there, we have a negative out front of the absolute value. We're just going to see that V shape flip upside down and then be an upside down V shape. So you saw that when you graph these things, hopefully. So make sure you just add on page 5 near the top where it says reflection. Just make sure you're adding the negative somewhere. So if you see a negative, you make that connection. Cease and desist. Whatever's happening over there needs to stop. Make it right, whatever it is. Sus. You sus. Y'all are sus. Again, I added some notes here just for you to kind of see what was going on between the parent and the children of this graph. We could go back to this later, but each transformation is shown in the actual graphs themselves and also then shown in the math that you can do to the parent y value to get the new y value as well. So I want to make as many connections as possible that this can be done algebraically without looking at the graph, but this also can be done just by looking at the graph. Page 6. Here's where we start to get a little bit more specific. I want you to make sure that this says a vertical stretch by a factor of A, and this is when A is greater than 1. Okay, so we're not talking about negatives. Negative is a reflection. So that's going to be a whole separate thing. You'll kind of see my notes here for Y4 especially. But every time that you have the V being like, I don't know, closer to itself, I don't know how to describe it. You're stretching it vertically. That's what's happening. Because the left and right sides of the V are increasing quicker, right? So think about this as a slope. The parent function is increasing as rise over run, 1, 1, 1 over 1, 1 over 1. As soon as you have a stretch, the graph is being vertically stretched up because you're going up, say, for Y2, you're going up, rise to run 1, rise 2, run 1. So you're increasing quicker as you go. Left and right. I apologize for the blinking. I don't know how to fix it. It has something to do with this connection, and I don't have another option. I'm going to give you some time to just read this, but I don't want you to try to jot it down. Just look at it, take a break with your pencil, and take a look up here, because I know this is what people do not have this written down. All right? So you don't have to try to like jot it down as fast as possible, but just look up here real quick. Okay, so when a equals 2, the linear portions of the graph increase twice as quickly. So you're going higher, faster, okay? When a equals 5, then it's getting super steep. Like nobody would want to climb those steps. Rise of 5, run of 1, right? And then as soon as you have a negative a, you're doing 2 transformations. So as soon as you see the negative, you know there's going to be a reflection. But then as soon as you also see that a is greater than 1, you are stretching this graph vertically, where now we have a decreasing situation where the rise is negative 3, 1, negative 3, 1, negative 3, 1. Just kind of look at the pattern. We are going to fill these things in our workbook too, so don't get too crazy with it. If you're multitasking or doing something else and you're not getting the point of this right now, I am telling you this is a little bit tough to keep track of, so make sure that you're keying in. Page 7. This one, you're now going to write vertical shrink by a factor of a. We might see the word compression, okay? I think that there's some sort of disagreement amongst mathematicians. Sometimes we see the word compression or shrink. This is where you're going to start to see, this is why I like to think of it as a compression, because you're like pushing down vertically on the V shape, and you're ending up with like a crushed V shape, sort of wider, because your slope is not as extreme. So here we're looking at values for a between 0 and 1, fractional coefficients for a. And you can think about this like slope, sort of. Okay, so don't tell me the slope is 1/2 for y2, because we're not really talking about a line right now. But we are talking about this V shape. Each side of the V is increasing by a rate of 1/2. Easily. These are actually used to model anything that bounces in this type of shape. It's a really good question. Pool tables, it's pretty much my main go-to, is to model like the way like trajectory of a pool ball goes. But I think also if you're thinking about like applied mathematics in terms of like everyone in here is going to take a physics class, and when you start to look at like how things behave, not just in absolute value, but like when we were talking about those parabolas as well, like the way that a ball travels, if you like kick a ball, the way it travels. And so like a lot of our physical world can be modeled by this stuff. And in order to kind of do that, you have to do like walk through this like stuff that doesn't make sense first, and then kind of see. I wish I had a better answer for you. But I guess just really try to get the pattern down. I don't know. I think it'll help later on in your life when you actually do have to solve problems involving like physics and whatnot. All right. Not to mention, I guess this is my go-to, is that when we are learning things, even if they don't seem completely applicable to like what we want to do for the rest of our lives, or like maybe we don't care about this stuff, which is totally fine. I just know that it doesn't really matter what you're learning, but in math especially, the more easily you can accomplish mathematical thinking, and the more you can master in your math classes, that actually directly translates to skills outside of school in general. Like people who are mathematically competent when they're graduating high school are more ready for like entering a career, even if it's not like you're not going to college first. And so just the skills of like, hey, I'm going to look at something over and over again and try to see what the pattern is and then make a generalization out of it. That is a skill that you're going to use even without realizing it. And I truly believe that. I do. I see it happen all the time. All right, so here you don't have to jot all this stuff down, but it's there for you. When a is equal to 1/2, the linear portions of the graph increase by half the amount as the parent.